Okay, folks, pretty much everybody should be done with the quiz by about now. I went ahead and looked at the results. You guys are doing really well, which is good. I mean, most folks, it seems, are getting most of the problems, and this is really good news. I'm seeing a nice uptick here with you guys, so that's good. You got a whole half a semester here left, a lot of points left in the course, so keep on chugging away. So we're seeing some good progress here, guys. Keep it up. All right, so we're into thermochemistry now. So the idea here is that we want to be able to use what we learned about in last night's video, which really kind of comes down to this idea of specific heat, right? So we're talking about a property of a substance or an object or whatever, where we're talking about amount of heat that it takes to raise 1 gram of that substance in temperature by 1 degree Celsius. Okay, so you can see how that's sort of a property of the substance. So some things absorb heat quite nicely, other things don't absorb heat as easily. So we're going to actually utilize that in calorimetry, which is where we're going to actually make these kinds of measurements. Okay, so let's define calorimetry first, and then we'll get into some specifics. So calorimetry, by definition, is the measurement of heat transfer in a thermally isolated environment. All right, there's 2 types of calorimetry that we can do, each using a different type of calorimeter. So the calorimeter is the device we use to make a calorimetry measurement. Okay, so the first type that we're going to talk about today is the so-called coffee cup calorimeter. That's the simple one. And then the one that's the topic of the next video is going to be the bomb calorimeter. That's quite complex. And my words mixed up. So let's talk about the coffee cup calorimeter first. That's the simple one. So let me just kind of get everybody on the same page first. You know what I mean by a coffee cup? What I'm talking about here is like a styrofoam coffee cup, like you might get from Sheetz or McDonald's or something like that, that they serve you your hot coffee in. Now, why would you want to have a styrofoam cup as opposed to, say, just a paper cup or a plastic cup or something like that if you're going to have hot coffee? Why would you do that? Anybody got an idea? Why use styrofoam as opposed to, say, paper or plastic?
It stores the heat in here.
Yeah, well, that's exactly right. You want to keep your coffee warm, right? Or hot. So the idea is you don't want the heat escaping from the coffee. The other thing, obviously, is that you don't want to burn yourself when you grab the cup. So you're exactly right. You want to keep the heat inside of the cup, okay? A thermos is a good example of this, right? So you can also put a hot or a cold beverage in a thermos. And of course, the idea is that the thermos either keeps the beverage cold if it's meant to be cold or hot if it's meant to be hot. So it basically preserves the temperature of the substance. And the reason for that is because it doesn't let heat in, it doesn't let heat out. Okay, so that's what we're talking about in the case of a coffee cup calorimeter. As a matter of fact, if you do these experiments in the lab, okay, and I think we used to do a calorimetry experiment in the bonding lab. I don't remember if we still do or don't. We used to do a coffee cup calorimeter lab. And the basic idea is that you've got this thing, this is your coffee cup, so it might be styrofoam. So something that is a nice thermal insulator. So it keeps heat in, right? Or keeps heat from coming in, whichever way we want to think about it. And then what I could do, for example, is I could fill this with something like water. Okay. And then a lot of times we'll cap it so heat can't really come in from the top. And then maybe we'll put a thermometer in here. Okay, because ultimately what we want to be able to do is to measure a temperature change happening inside the calorimeter. Okay, And then the idea here, for example, is we can run a reaction in this. So this could be a chemical reaction or a dissolution or something like that that happens in aqueous solution. Now, the idea here is that the whole calorimeter becomes our thermochemical universe. Now, remember, in thermochemistry or thermodynamics, the universe is made up of the system and the surroundings, right? So the whole universe is contained in the calorimeter. So in this case, the reaction would be the system. And the solution that houses the reaction becomes the surroundings. All right, so the idea here is that if I have a reaction that gives off heat when we put it in aqueous solution, what's going to happen to the temperature of the water? Well, it ought to go up, right? And we're going to register that in a temperature change before or after of the thermometer. So the thermometer is going to allow us to measure a delta T, or change in temperature, T final minus T initial. All right. So then ultimately, we should be able to get back to, by using specific heat arguments, the amount of heat that got given off by the reaction to the water. That's the basic idea here. Okay. Another simple way in which we might use a coffee cup calorimeter is to determine the specific heat of, say, a particular substance or object. So that's the purpose of example number 1 here. All right. So this is a simple coffee cup calorimeter kind of problem here. So let's read through it and see what's going on. All right. So I've got a 465 gram piece of iron. Okay. And I'm going to put that in an oven and get it hot. All right. So then once it's hot, I'm going to take it out of the oven and I'm going to dump it into 375 grams of water in a coffee cup calorimeter. Okay. So it turns out now in this case, since the iron is the hot object and I put it in the water, what's going to happen? Well, the iron's going to give up heat to the water until what? What's going to basically cause that to stop? Okay, what has to happen for that heat transfer to essentially stop between the iron and the water?
Thermal
Or how do you know
equilibrium.
it's? Yeah, you're going to get to thermal equilibrium. In other words, the temperature of the mixture is going to come to a constant value. Okay, and that means that the heat transfer is essentially stopped. Okay, so it says the temperature of the water increases from 26 degrees Celsius to 87 degrees Celsius. So that 87 degrees Celsius is that point of thermal equilibrium where the temperature of the iron is equal to the temperature of the water. All right. It tells me that the specific heat, that's the C there for iron, is 0.449 joules per gram degree Celsius. And if I know that, I want to determine the original temperature of the iron when I hauled it out of the oven. Okay. So this is a good sort of thermodynamics problem for us involving a coffee cup calorimeter. So let's determine sort of equation-wise what we know. So we can always go back to the equation that we introduced in the video. And that says that Q is equal to C times M times a delta T. All right. Now remember here, C we just defined as the specific heat. Okay, that's the essentially the amount of heat that it takes to raise 1 gram of a substance by 1 degree Celsius in temperature. M is going to be the mass of the substance, and delta T is the temperature change that the substance undergoes. Now, if I want to, I can define a Q for both water and iron, because those are the two substances that are involved in this matchup, if you will, that's happening inside the calorimeter. So what I can say here is to get to thermal equilibrium, right? I can say that the Q associated with the iron has to equal to the Q associated with the water. In other words, the heat transfer from one to the other has to be equal. In other words, the heat has to leave one thing and go to something else. All right. So the other thing I have to introduce here is a sign, right? Because again, the heat is flowing from one place to someplace else. So wherever the heat is flowing from is going to get a negative sign. The substance that heat is flowing to will get a positive sign. And that makes sense, right? Because heat is leaving an object, its internal energy is going down. So in this case, it's the iron that's cooling off and it's the water that's heating up. So I'm going to need to put a minus here in front of the Q for the iron. The heat is leaving the iron and going to the water. Does that make sense to everybody? So this is the premise for any calorimetry experiment. It's a simple transfer of heat from one substance to another. Okay, and I can quantify that through the equation up there at the top. Q is equal to C times M times delta T. So I could do a simple substitution and write this. I could write minus C for H for the Fe times the mass of the iron times the delta T associated with the iron is going to equal to positive C for the water times the mass of the water times the delta T, or change in temperature experienced by the water. Okay. Now I could do one other thing, because what am I trying to get at in the problem? I want to get at the original temperature of the iron. So that's going to be the T initial of the iron. So remember, I can always define a delta T for any substance as the T final minus the T initial. That's what a delta T is by definition. So I'm going to make one more substitution in here before I really get down to the algebra. So I can say minus C for the iron times the mass of the iron. Now the delta T becomes the T final minus the T initial. And I'm going to put a little Fe down there for the iron. All right, and that's equal to C of the H2O times the mass of the H2O. And again, I'm going to represent my delta T as T final minus T initial, in this case, of the water. Now, why did I not need to specify the substance when I put the T final there? Why is it the same T final for both?
Because they're both the same temperature.
Yeah, because at the end of the heat transfer process, remember, we reach thermal equilibrium. So the temperature of the iron has to equal the temperature of the water. So I can just let that be a TF, right? And that's all that means is it's the final temperature for both. Okay, so now what variable is it that I'm after here? So the question asks, what was the original temperature of the iron? So the variable that I want is that guy right there. Okay, it's the T initial for the iron. Okay, so now basically what we have to do is we got to do a bunch of algebra. Now, I'm going to go ahead and just give you the result of the algebra. You guys probably ought to make sure you can go through it and get the same result I've got. But essentially what I end up getting here is T initial for the iron is equal to the C of the H2O. And again, there's several ways you can solve this thing. Mass of the H2O times the T final minus the T initial of the H2O. All right, all of that divided by the specific heat of the iron and or I should say the heat capacity. There's really two ways to define C. Sometimes I call it specific heat. Sometimes I call it a heat capacity. They're basically the same thing. So sometimes I slip and I use those two terms interchangeably. I'll try to say specific heat because that's what the book uses. And the mass of the iron. And then you end up having to add to that the T final. Okay, so now you just plug everything back in. So when you do that, the specific heat of water is what, 4.184 joules per gram degrees Celsius that we introduced in the video. And that's basically a number we use over and over and over again because we use water all the time. Times the mass of the water, which is 375 grams. We want to make sure all the units work out here. And what's the delta T of the water? How would I determine the delta T of the water? Let's go back up and look. Oh, looks like the water increased from 26 degrees Celsius to 87 degrees Celsius. So what do I have to do? I have to take the difference between those two. And when I do, I get 61 degrees Celsius as my delta T. Okay. and come through and divide all that by the specific heat of the iron, which the problem gave us. That was 0.449 joules per gram degree Celsius. All right, times the mass of the iron, and we said that was what, 465 grams. And then we have to add to all of that the T final, which is 87 degrees Celsius. Okay, so let's make sure the units work out. So all that stuff lumped over on the left should be in degrees Celsius, right? Because it has to add to something that is in degrees Celsius. So looks like all those specific heat units cancel. Looks like grams cancel with grams. Oh, and looks like Celsius adds to Celsius, and that's good. So the T initial that I get here turns out to be 545 degrees Celsius, which is pretty hot. So that's the initial temperature that the iron had to be at for this whole process to happen, to give me the required delta T for a given mass of water. Okay, so you see the basic idea of what we did here. The setup for every calorimetry experiment is always going to be the same. And the key thing that we have to always remember whenever we do any calorimetry experiment is that heat is going to be transferred from one species to the other species. That's always the premise that we're going to make. Okay? Any basic questions there?
4.184 joules at the top of this.
Yeah, the 4.184, this number right here. That's the specific heat of water. So it's actually this. Okay, so that's a very well documented quantity, and we actually did. It's not given in the problem because that's, again, one of those numbers that basically you just go look up, and we use it so much that essentially we just always memorize it. So water is always kind of a reference point for a lot of these calorimetry problems that we do. We did introduce that in the video as well. Okay, but that's what that corresponds to, even though it didn't show up in the problem. Usually that's not given in the problem because we use it so much. So it's kind of like one of those constants like Avogadro's number or something that just gets used so much that it's left out of problems. Okay, so let's look at another situation here, guys. We could also do a calorimetry experiment for a chemical process. This could be something like a chemical reaction or a dissolution or something like that. And that's what's going on in this situation. All right, so what we've got is 0.75 gram sample of potassium chloride, which is just a salt. I'm going to dump that into 35.0 grams of water, again in a coffee cup calorimeter, and I'm going to stir it up until it dissolves. So really what we're looking at here is the heat associated with the dissolution of a salt, okay, or the solvation of a salt. Now, when the salt dissolves, it says the temperature of the solution drops from 24.8 degrees Celsius to 23.6 degrees Celsius. Okay, so the question is the process endothermic or exothermic, where we're focusing on the actual reaction associated with the dissolution of the salt? Okay, so remember, the whole universe is inside the calorimeter. And what's happening? It looks like the solution itself is cooling down. Okay, so would you call that endothermic or exothermic from the point of view of the reaction, which is the system?
Endothermic.
Yeah, because heat's flowing into the reaction. You're exactly right. It would be an endothermic process because heat is flowing into the reaction. It's flowing out of the solution, which houses the reaction, which is the surroundings, and into the reaction. Okay, so what we actually see is a decrease in the temperature of the overall solution. Okay, so that would indeed be endothermic. So in the end, our Q value that we should get from this process should be positive. So Q, as we calculate it, should be greater than 0 for an endothermic process. Remember, that's one of those sign conventions that we talked about. All right, so the question is, what's the heat of the solution of the KCl expressed in kilojoules per mole of KCl dissolved? Okay, so again, we can set this up in terms of the Q of the solution, and I'm just going to call it water here just to keep things simple. I realize it is actually a solution because it has salt dissolved in it, is equal to the Q of the reaction. Okay, now what did we say? we said that heat is actually leaving the solution and going to the reaction. So my Q has to be on the water or solution side. All right. So now what this means is that I can also use my equation for specific heat here. And I can put it in terms of water, can't I? Because water now is basically where the heat is leaving from. Okay, so now I can put this in terms of Q reaction. Q reaction is equal to minus Q of H2O, which I can also rewrite as minus C for H2O. And again, I'm assuming here that the solution's heat capacity is the same as water's, times the mass of the water, times the delta T of the water. Okay. So let's go ahead and set this up. Specific heat of water is minus 4.184. That's joules per gram degrees Celsius. And then I got to multiply that by the mass of the water. Now at this point, it's kind of up to you whether you guys want to add the mass of the KCl in there or not. You could make it 35 grams for the water, or you could make it 35.75 to express the mass of the solution. So it kind of depends on the problem, whether you do that or not. I'm just going to keep it simple and leave this as 35 grams of water. And then what's the delta T? Well, it's the T final minus the T initial. And since the water is actually getting cooler, that turns out to be a negative value of 1.2 degrees Celsius. Okay, so look what happens here. The negatives cancel each other out, which is what you'd expect to happen because I need to get a positive Q out of this thing. The degrees Celsius is cancel. I'm left with joules, which is heat. That's what I need. So I get 175.728 joules, and they want it in kilojoules. So let's go ahead and convert it to that real quick here. So 1 kilojoule is 1,000 joules, right? All right, so that turns out to be 0.175. We'll get sig figs here in just a second. 728 kilojoules of heat, positive. All right, so it looks like I'm limited to 2 sig figs by my temperature. So I'm just going to underline those first two to recognize that's my sig figs here. Now, it asks for one other thing here, guys. It wants the kilojoules per mole of the stuff that I dissolved. So I need to get moles of the KCl. So let's just go ahead and do that as an aside step. 0.75 grams of KCl. Let's just convert it to moles because we know how to do that. So 1 mole of KCl corresponds to 74.5313. That's from the periodic table. Grams of KCl. Okay, so grams cancel with grams, and I'm left with 0.0100602 moles of KCl. Okay, and that's going to be good to 2 sig figs, so 0.010 really. So now I can get kilojoules per mole, right? So now my Q for my reaction, if you will, in the correct units, is going to be the heat, which is 0.17527175728. There we go. Kilojoules of heat, positive, divided by the 0.0100602. Notice I'm keeping all of those digits. I can get my sig figs later. Moles of KCl. So I'm good to 2 sig figs there, 2 sig figs there. So I end up with 17.4676. And that's going to be kilojoules of heat per mole of the KCl, okay? And that's going to be good to 2 sig figs. So I'd actually report that out to 17 kilojoules per mole. And it should be a positive value because, again, the heat was flowing out of the solution or the water and into the reaction. Okay, so see how I pretty much set this up exactly the same way as I did the prior problem. But now we're just talking about a reaction. Okay, any questions about this before we do a little practice? All right, let's go to Chem 101 real quick, guys. And I got just a little bit of practice for us to do, just 2 problems. So simple calorimetry, let's start it. And we're good to go. So it's really just a simple specific heat kind of problem, and then just a little calorimetry problem that we worked here. So see how far you get in the next few minutes.
Professor, quick question.
Sure.
Under calorimetry, what does the
Hmm?
second bullet point say?
Under calorimetry, I'll have to jump back real quick and see. Let me go back to my notes. Right there?
Yes.
All right, so it's a coffee cup calorimeter, which is the simple one. And the second one is the bomb calorimeter, which is the complex one. That's the one we're going to talk about next time's video.
Okay, thank you.
You're very welcome. Good. Looks like a couple of you are making it over to part 2 here. That's good. So yeah, I think you guys are seeing that the setup for that second problem is really similar to the setup for the first example problem. You're just kind of solving for a different variable this time, right?
Could you do number 1, please?
Sure. So we want to know the specific heat. You're gonna have to like feed me the info. I'm working off one screen today, but I want the specific heat of an unknown metal. So if I go back to that. All right, so my equation is this, right? Q, I always start from the same place, is equal to C times M times delta T, right? So I want to know the specific heat for the metal. Wasn't that what the question was asking? So I got to solve for C, don't I? So C is going to equal to Q divided by, let's see what it is, mass times the delta T that the metal undergoes. Okay, so does the problem give you a Q? Probably does. And it probably gives you a mass and it gives you probably a temperature difference. So really,
Yes, the mass was 75.01 and the temperature was 45.2 degrees Celsius.
that's the delta T. And what was it?
Yes,
What was it again?
45.2.
Okay. And did they give you the mass of the metal?
The mass was 75.01. The Q was 1870 joules, 1,870 joules.
Oh, what was the, I don't know what the 75.01 was. Okay. I'll go back and look real quick. I can toggle. Okay. 1870, right?
Yes.
Okay. And that was joules, wasn't it?
Yes.
So yeah, basically you just plug in those numbers in right there. And you should get your C back out of that. You should get units of joules per gram degree Celsius. That should do it for you.
Thank you.
You're welcome.
Can you do number 2 as well?
Yeah, we can do the setup real quick. Again, let's just look at it real quick, blah, blah, blah. Okay, it looks like a metal going into water. And again, you're gonna have to feed me some information here. Okay, so the setup on this is gonna be the same thing. It's gonna be the Q of the metal is gonna equal to the Q of the H2O, right? And the metal started out hot and it got cold, didn't it? So I should have a negative there by the metal. Okay, so now let's go ahead and plug everything in. Minus C for the metal times the mass of the metal times the delta T of the metal, which I'll just go ahead and call the T final minus the T initial of the metal, has to equal to the Q of the H2O, which is the C for the H2O, right? Times the mass of the H2O times the delta T of the H2O. So that's going to be T final minus T initial for the water. Okay, and what were we after? We were after the specific heat of the metal, weren't we? Okay, so if we solve this, this is actually pretty easy to solve. I want C sub M, so that's going to equal to, I'm going to carry the negative over, minus C for the H2O times the mass of the H2O times the delta T of the H2O. Which you can go off to the side and calculate because I think you have all the information for that. And then what are we going to divide by? We're going to divide by the mass of the metal times the delta T of the metal, which is the T final, which is the equilibrium temperature, minus the T initial of the metal. Okay, so then you would just plug all your values into that. Now what's going to happen? You're going to end up with a T final minus a T initial on the metal that's going to be negative, right? Because the metal starts out, or the other way. Yeah, T final. Yeah, because the metal starts out hot and gets cold. But look what happens. you can't have a negative specific heat, but look what happens there. The negative out front cancels with the negative that you get in the denominator, so you end up getting a positive specific heat for the metal. So there's your equation. It's just now a matter of sticking the values into it. Does that help?
Yes, thank you.
Perfect. All right, so I think we're about out of time. Make sure you guys go back and look at the video for bomb calorimetry and be ready for a 5 for 5 on Monday then. And have a great weekend, guys.
You as well.
Professor, I have a ROTC event on Friday, so I won't be
Okay.
here for the Friday quiz. Would you like me to make it up like some other day, or like maybe like do it Thursday or do it like Monday?